Hey guys, welcome. Yeah, so a while back, I shared a video on Euler's method where I give you a thorough discussion. So if what you want is the A to Z of Euler's method with every single detail in it, then watch that video. If on the other hand, what you need is a crash course or a quick review of Euler's method and how to solve a problem on it, then this will do just that. Now, this comes from the 2016 AP Calculus BC FRQ, and it's problem 4, part D. In a different video, I showed you how to solve parts A through C of the same problem, and there in that video, I had promised that I'd make this video, and so then promise kept, right? Okay, all right. Now, quickly read the question, and things to highlight are that y is equal to h of x, and the derivative of h, dy dx, is given by this expression, and that the point 0, 2 is on the graph of h. That's what this is saying. And we're using Euler's method starting at x equals 0 with 2 equal step sizes, right? Okay, and we're doing that to approximate h of 1. Now, of course, we use Euler's method because we're saying for one reason or another, we can't solve the differential equation, and therefore we're unable to figure out what function y gave birth to this differential equation, right? Okay. All right, so how does it work? Well, as you can imagine, I'd already done this problem before with students, and so I know that the graph of h doesn't look like this. In fact, we don't know what the graph of h looks like, but the graph of h should be, in this specific problem, decreasing, as you will see a little bit later. However, I drew an increasing function because, well, for the point that we're trying to illustrate, it doesn't matter if I draw this kind of a function or whatever other function. Again, we don't know what h looks like really. Okay, cool. So this is the whole point, right? So we know that the initial point is 0, 2 on the graph of h. So that's like right there. So 0, 2 is on the graph of h. And of course, the blue curve I'm claiming is h. Fine. So what we do is we start off with a tangent line, right? Since, first of all, let me backtrack a little bit. I'm not following. I'm like speaking off of the animation. Like I'm not in sync with the animation. So let me do that. So since we're trying to get to h of 1, right? We need to go all the way to x equals 1. But since we're using 2 steps of equal size, then we step on 1/2 to get to 1, right? Okay, that's what that's saying. All right, so the way we do it is we take a tangent line. I was just eager to like get started, right? The tangent line at 0, 2, and let's call that t sub 1, meaning our first tangent line. Now, if you're using 2 step sizes, you're going to need 2 tangent lines. If you use 3 step sizes, you're going to need 3 tangent lines, and yada yada. Use your imagination how that count would work. All right, but now, so we've got t sub 1, our first tangent line at 0, 2. Now, in slope-intercept form, or rather point-slope form, this is the equation of a line, right? You need a point, x1, y1, and then you need the slope m, right? Okay, so the point we already have, and that's x1, y1 is 0, 2. Got it. And for the slope, we need to evaluate dy dx at this point. So we evaluate dy dx at 0, 2, and that's easy enough. Plug in 0 for x and 2 for y, and simple arithmetic will say that the slope of this first tangent line, t1, is -1, right? Just making it abundantly clear what we're plugging in there. But otherwise, it's, as I said, simple arithmetic, and this is the arithmetic. Okay, cool. All right, so now we could write the equation of t sub 1 in point slope form in this form, and that's just substitute for x1, y1, and m. And when we do, what we're going to get is that t sub 1 is equal to this here, right? And I know most of us are used to figure not drawn to scale, right? Okay, most of us are used to the point slope form, the slope-intercept form rather. So if you convert the point slope form to the slope-intercept form, it'll look like this. That way, you know, we can readily plug in the x value and get the y value for what? For 1/2, because, well, since we don't know what this function, this blue function h is, we don't know what h of 1/2 is. So we need our second point, x2, y2. x2 is simple enough. Since we're stepping onto 1/2, x2 is going to be 1/2. But how are we going to find the corresponding y value? Again, we don't know the function h, so we can't plug it into h. So what we do is we find the corresponding y value to 1/2 using t sub 1, because locally in this part, right, near 0, t sub 1 does a pretty good job of estimating values of h, right? Okay, cool. So x2, y2, as I said, x2 is just 1/2. For y2, we plug in, and I'm just showing you that like the real y value is right there, but we're going to use this y value instead. And so that's the y value for the tangent line t sub 1. And so then we plug in -1/2 into t sub 1, and so that it looked like that, meaning the y value approximated by t sub 1 for the function h when x equals 1/2 is 3/2. So we have 1/2 comma 3/2 is our second point. Got it. Okay, so then what? Well, we go to our second tangent line. So our second tangent line we know is going to be like that. Yes, it's kind of funny to call it a tangent line because it's not even on the curve h, right? But it's fine. It's still a tangent line in theory, right? And of course, what this tangent line crucially does is it course corrects. Because like if we tried to use t1 to approximate h of 1, it's really off. Look at the trajectory of t1. It's going to be like somewhere over here. That's way far off like what the curve says, right? And so we course correct with the second tangent line. And of course that means that we need to find the new slope for t sub 2. And we already have the points for t sub 2, and that's 1/2 comma 3/2. So all we need is the new slope at these two new points, 1/2, 3/2. So then substituting again into dy dx, but this time the x value 1/2 and the y value 3/2, we do this arithmetic to learn that our new slope for t sub 2 is -2/4 or -1/2. Yeah? Okay, cool. So t sub 2 then is going to be, again, point slope form. This is pretty straightforward. We've been through this. So it's going to look like that, and simplify a little bit to get it into the slope-intercept form. So that'd be this, right? And, well, we're not done, sorry. I needed to add this over to the right side, right? Otherwise, what I had done before is just distribute this -1/2, and that's why I got this fella and this fella, and adding this over and making sure that I have a common denominator. That's simple arithmetic, but I just want to help you out in case you found that confusing. So this is what the equation of t sub 2 is. All right, got it. Now, so as I said, if you have two step sizes, the second tangent line is all you need. And so then we just plug in x equals 1 into this t sub 2 equation right here to learn that h of 1 is approximated by this value, -1/2 times 1 when we plug in x equals 1. And well, that bit that I rushed through, well, I'm just showing you that like that's the approximation of h of 1, right? Onto t sub 2, and it's pretty good. It's pretty good. And so that's that, right? And I'm not much of an arithmetic fan, as you might have heard me say in previous videos. So you can finish the task. That's just -1/2 plus 7/4. But otherwise, you know, the only thing I'll say before we conclude is obviously if you use more step sizes, there are more course corrections, and so you'll get a better approximation of h of 1 the more step sizes that you use, right? Like, so sorry, the more steps you use. So the smaller the step size, the better the approximation of h of 1 will be. All right, cool. I hope you found this helpful. Otherwise, I hope you're well. And yeah, keep watching. Take care.